Today's presenter is Elliot Samuels, CADfix Viz product expert. Elliot, I will turn things over to you.
Thank you, Kristen. And hello, everyone. I'm Elliot Samuels. I'll be your presenter today. I'm an application engineer at ITI, based in our UK office in Cambridge. Today, I'm going to be presenting CADfix Viz. So all the CADfix products are sort of focused around CAD interoperability. The reuse and sharing of our mechanical CAD data and repurposing that from a variety of different things. CADfix Viz specifically, as you can see, is about converting CAD to VR, or more generally, visualization ready mesh. So CADfix Viz. What is CADfix Viz? CADfix Viz is a CAD to mesh conversion solution that maximizes the reuse of 3D digital assets for visualization applications. Particularly relevant for virtual reality applications, but also more generally for web and mobile and applications where we need to visualize large amounts of data in maybe even a desktop application where you might have a plant layout and you have lots of models and you're trying to visualize all that at the same time. It's important to produce lightweight, low triangle mesh representations of our quite complex BREP mechanical CAD models. And as always, there's the obvious benefit to process automation. We want to streamline this conversion process as much as we can. So CADfix Viz helps to do this conversion with a full automation and batch capabilities. And what does this give us? So CADfix Viz reduces the manual work associated with prepping CAD models, large complex CAD assemblies for use in visualization applications such as VR, AR, MR softwares, and as I said, web and mobile. The multi-CAD and multi-mesh import and export allows users to seamlessly move from sort of the CAD space to the visualization space, taking native CAD files into various applications downstream. And as I said before, automation and batch capabilities reduce this time spent repurposing complex CAD for use in our downstream applications. So bringing CAD to VR. Engineering firms produce large, complex BREP mechanical CAD models and CAD assemblies. Visualization requires mesh models, faceted models, more lightweight representations that we can render on screen. And in the case of our visualization applications, such as VR, mobile and web, we're often limited by the complexity, file size, and the poly count or the triangle count of our models. So this second stage in this flowchart here, the mesh generation, optimization, and CAD rework, is a bit of a bottleneck at the moment in this process. We want to sort of eradicate that bottleneck so we can quickly convert our complex CAD and bring that into our VR visualization world seamlessly. And that's where CADfix Viz fits in. So CADfix Viz, our software solution, has a number of different things. So multi-CAD import and mesh import, obviously crucial for the interoperability. CAD repair, assembly optimization, mesh generation, model defeaturing, and intelligent mesh decimation are all sort of key components and probably make up the discussion of 80% of this presentation. And again, key for interoperability, the multi-format mesh export, export to multiple levels of detail, and full attribute support. So support for assembly structures, support for colors, layers, labels, and associated CAD metadata. And we have all of this wrapped up into some interactive tools and an interface, so you have close control over the process. But also, as I've already said, it's very important that we have process automation to streamline this as much as possible. So when we wrap all of those things up into our process, what we're looking to achieve is this reduced triangle count and mesh file size via our defeaturing. So here, a real example, we have our complex BREP CAD model, lots of features. We can turn this into a visualization mesh. Here we have quite a complex mesh. We've just meshed this as it is, all the components, all the small bodies, and all the features. and we have a huge model, 424,000 triangles, not particularly appropriate for our visualization application. And then using our CADfix tools, we can turn this into a more appropriate defeatured mesh, retaining a lot of the visual aspects. You can still see it's the same model taking up the same space, but we've massively reduced this down to just 8,898 triangles. So that's going to render much faster. And when you have a lot of these models in the same application, that's obviously going to build up. So much more appropriate model at the end of our processing. And we want to do this obviously automated. So CADfix Viz fully automates this conversion and simplification process, including the generation of multiple LODs. And this can be set up using any combination of the tools and settings and tolerances that the user deems necessary to ensure that we always get the right level of detail for our application. That's obviously specific to us. And we can do this from the command line. So we have command line batch capabilities so that we can integrate this into complex workflows and do sort of mass CAD to mesh conversion without having to have that human interaction with the software. So this is another example of where we've used our automatic batch capabilities. We've taken in a complex BREP CAD and we've produced 3 levels of detail here. The first one, very high quality, very, very dense, 1 million triangles, probably only really appropriate for static rendering. Then we have our LOD 1, much more appropriate for something like a visualization application, with a sort of a fifth of the original triangles, and then a more crude LOD 2 mesh for for looking at things from further away, or when you're integrating that with a number of other components. So that's sort of a high level overview. So we'll break that down now into sort of the key functionality and go through sort of step by step the standard sort of processing that we would do. So the first part of any process is the import. So as just to reiterate, as it's a interoperability software, and that's the focus, we obviously have to be able to take in models from various places. So we have full support for reading native CAD files, so CATIA, NX, Creo, Inventor, Solid Edge, and SolidWorks, part files and assembly files, as well as the obvious neutral CAD formats, so STEP, Parasolid, JT, and DWG, and also our mesh formats, obviously widely used in visualization. FBX is a common one, as well as GLTF and OBJ. Another key aspect of the software is mesh generation. So we obviously start off with our complex CAD, and we need to turn that into meshed models. The first step in this process is the CAD repair. So CADfix can repair CAD faces to prevent mesh failures. So when you have very complex geometry, sometimes it's hard to mesh. We can automatically repair the model to prevent any of these mesh failures, as well as some other stuff. So surface conditioning, merging operations to merge duplicate geometry, and as well as some other things. This example here on the right-hand side shows a model where this dark component has poorly oriented normals, so we have to reorient them so that we have a nice shaded model. I mean, effectively, this is showing a component which is inside out, so it's shading badly. Our CAD repair process can identify these issues and fix them so that we're always left with nice meshed models. And then obviously, once we've repaired our models, we have to generate the mesh. So we have accurate, high quality, watertight mesh generation capabilities. We always produce the minimum number of triangles to capture the geometry within defined tolerances. And this in turn creates, models of the minimal file size, which is key. We have full user control over the accuracy settings, so our sag and turn values. And also we have the capability to go and select a number of components or sub-assemblies of a large model and mesh these individually, so you can break down large equipment assemblies into sort of key components or sub-assemblies and mesh them, and be left with sort of multiple different files at the end containing different parts of that model. So defeaturing mesh, as I said, this will make up the majority of the presentation, and it's a very key part. What we're left with after generating our mesh is often quite complex mesh with lots of triangles. not appropriate for our visualization applications. So what we do is we do some defeaturing to reduce that complexity, triangle count, and in turn the file size. So there are a few things we do. The first is removing unwanted parts. So that's identifying and removing small bodies automatically, as well as removing internal features, which is quite key often in visualization. You're looking at a model from the outside, there's lots of complex details and lots of triangles contained within the inside of the model that the user can't see. We want to get rid of those. We can remove unwanted features, so CAD features such as holes and protrusions. This is very fundamental for software. This is where we see a lot of big losses in triangle count by removing small holes that you can't really see, or they're covered by bolts, and they add a lot of complexity to the mesh. And we can also do some more crude simplification by wrapping components. So we have a couple of different wrapping settings, and I'll explain those separately in a few slides. And then, as I said, all these simplification tools can be run automatically or interactively for greater control over the results. So we'll start with the removal of unwanted parts. First one is removing small mesh bodies. So as you can see on the right here, we have a gearbox, and we have lots of small nuts, bolts, and we want to get rid of those because they're small, they're insignificant to the general shape of the model. So we can automatically identify and remove any component under a specified size. Secondly, removing internal features. As you can see on the gearbox here on the right, there's a lot of complex CAD on the inside of that. Those gears will require lots of triangles to mesh. So we can automatically identify and remove internal components, ignoring holes under a specified size. And this automatically removes interior triangles of partially internal components as well. So as you can see on this gearbox, there's a shaft extending from the inside to the outside in the bottom left. And what we've done is we've retained the end of that shaft, but we've removed all the triangles on the inside to ensure that we're minimizing that triangle count as much as we possibly can. Moving on to the removal of unwanted features. And firstly, the holes. We can automatically find and remove holes. Small holes add a lot of complexity. If you look at these pictures on the right, where I've isolated a couple of components, you can see the before and after of removing those holes. Where you have these small holes, you have lots of curvature, and the accumulation, it really builds up. So the cumulative effect of removing multiple holes is significant, and we can filter these holes based on type, shape, and size. So as I said, the cumulative effect is significant. So as you can see in this small model here, where we've started with 7,000 triangles, we've removed the small holes. The model looks very similar to before, but we've gone all the way down to 2,700 triangles, which is much easier for us to render in real time, or integrate that model with a load more models in another application. The second removal of features is protrusions. So we can automatically find and remove protrusions, very similar to the holes. As you can see in these images, they add a lot of complexity. This thing on the right here has a lot of embossed text, and embossed text adds a lot of complexity where you have to have lots of triangles to capture all that curvature and all that extra detail, which we just don't need. So we can search for the protrusions and basically wipe them from the surface, and that leaves us with a much simpler model with a lot less triangles and something much more appropriate for our visualization application. And moving on to our wrapping tools. So we have a number of options for forming wraps. The first is a box. I mean, it's fairly straightforward and self-explanatory. We can turn things into a box. So that's just 12 triangles, obviously. And so maybe see on the top right here, we have this very complex component with lots of detail on it, and we can just turn that section into a box. It reduces a lot of the detail, but we still have sort of a general shape. We also have some wrapping tools such as convex hull wraps and shrink wraps. The best way to describe these is just to look at these pictures here. So on the left, we can see we have our sort of a pump and motor system. In our original mesh, we have 80,000 polygons. That's quite a lot. 2 megabyte file. By using our shrink wrap, we can see we've sort of moved over the surface of those cooling fins, and there's some grating on the back of that motor. So the shrink wrap retains sort of more detail, but as you can see, we've still reduced that down to sort of 9,000 triangles and massively reduced the file size. And again, a slightly more crude representation is the convex hull wrap. And as you can see there, we have, that's appropriate for sort of a low level of detail with sort of minimum polygons and a very, very small file size. So there are defeaturing tools. As well as our defeaturing tools, we have some intelligent decimation algorithms to further reduce that triangle count. I think to explain this, I'll move on 2 slides just to explain decimation a little bit. So decimation doesn't actually do any defeaturing. It doesn't remove any features from the model. It doesn't remove any components. What it will do is it will take areas of high complexity like this, and it will swap out triangles to form a more crude mesh. So we have our intelligent decimation algorithms, and we have multiple constraints to allow close control over this decimation process. We say our decimation is least destructive. So what that means is we can prioritize the decimation of complex areas to achieve the maximum triangle reduction for the minimum geometric change. We can set a maximum geometric change as a safeguard against excessive decimation. We can set target values for the decimator to aim for, so very useful for sort of polygon budgeting if you're making sort of a VR application where you have a certain number of triangles that you're aiming for, and we can sort of aim for a percentage reduction on each component or set a maximum triangle count. And we can use these targets, the percentage reduction and the triangle count, across the whole model. So you can say, I want to get rid of 70% of the triangles in this model, or you could say, or you could apply those to individual components or a selection and say, right, maybe I only want 1,000 triangles is my maximum for each component. So just some examples of this. Here we have this bike frame, and we've done some decimation, and we've reduced the triangle count by 70%. As you can see, where we have like large curves, it's slightly more jagged, straight edges, but still very closely aligns with the original model. And similarly, this mesh decimation to a target triangle count. Here we've gone from 195,000 triangles to 20. This is an excessively complex mesh on the left. It doesn't need to be that nice. Obviously, with that number of triangles, we have nicer shading of the model, and you can see that between the one on the left and the one on the right. But for our purposes, we need to reduce that triangle count, and this is a really good way of doing so. And then at the end of the process, obviously, we want to export our models to one of the visualization formats. So again, key to any interoperability software, we have multi-mesh format export support. So you can go to one of a number of different file formats. We have custom flavored FBX exports for Unity and Unreal software. We can export our single or multiple LODs to one or multiple files. We can export the whole model, or we can export just a selection of components or a specific subassembly into a file. And again, this can all be achieved through the automated process. What we've tried to achieve with this, so being able to export different lots of different files and selections, is just to be as flexible as possible so that you can always have what you want in your files at the end of the process. And here's just some examples of the format. So FBX, very commonly used, I've already said, GLTF, JT, OBJ, flavored FBX for Unity software and the Unreal Engine, VRML, and XGL, ZGL. So I think that's enough of the slides. That's just some sort of a high-level overview of the functionality in CADfix. So what we'll do is we'll move into a demo, and we can see the software in action. I've pre-recorded this just so I could skip out any processing time, but I'll try and highlight how long the processes took. They're not very long, but it's just better than sat waiting around for them. So here we're in CADfix Viz, and we'll open up a model. And what I'll do is I'll mesh this model. I'll run through the interactive tools first, one by one, just to show sort of each tool in action. And then I'll go back and show you how we can achieve all this automatically to create multiple LODs, sort of with minimal user interaction. So as you can see, we have our BREP CAD model on screen, and I'll just shade this and then walk you through the interface. So I'll start by opening the assembly tree. So as you can see, we have full support of the assembly structure. You can see we have 49 parts in this model and 6 sub-assemblies. And here we have a list of all the individual bodies which make up this model. So these are obviously instantiated in that assembly structure. On the left-hand panel, we have a number of tools. So here we have our create panel. From here, we can generate our mesh at our different levels of detail. And just underneath this, we have our simplification tools. So as you can see, there's the same tools as I've just ran through in those short slides. And this is how we can process our model interactively. So let's start by generating some mesh for this model. So we'll create a LOD0 mesh, so quite a complex mesh with lots of triangles. So sort of suitable for static rendering or just a high quality model. As you can see, we've meshed that now, and we can see all of our triangles on screen. And as you can see, this has appeared in our mesh list at the top. So here we have mesh 1, it's LOD0, and we can see we have 41,712 triangles making up this model. And now we can open up our mesh tree now that we have some mesh. And you can see how many triangles are used to make up each body. So we have this component here is 4,412, and we can use this tree to select and sort of interrogate our model and find out where we have areas of high complexity. And again, this is really useful for sort of polygon budgeting when we're looking to reduce complex components which are, too detailed and causing issues with rendering the model on screen. So we have our complex mesh. It's too complex for our purpose. We want to reduce this triangle count and we want to reduce the file size. So let's start by simplifying this model. What I'll do is we can copy this mesh from the top. So now we have another mesh 2 in our list, and we'll simplify the second mesh so that we can, compare our defeatured mesh with our original mesh as we go. So the first thing we'll do is remove small mesh bodies. So as I said, what we're looking to do here is find things such as nuts, bolts, and washers. So to do this, we can use a hard value. So we can say anything under a bounding box of 10, 15 millimeters, or we can go in and select components on screen, and that will return, the size of some components. So let's just measure a few of these bolts. And we decide that that's an appropriate value for us for this model. So I can press OK, it will return that value, and all we have to do is hit find. And all the small components under that specified tolerance appear on screen. So we found 16 small mesh bodies. Obviously, there's a lot more highlighted, so 16 bodies and all of their instances. And we can hit fix, and it will remove those from that mesh set. As you can see, we've gone down to 36,480 triangles. So the next tool we'll look at is the remove holes tool. As I said before, a really key piece of functionality. We see massive gains from using this tool. So if we remove some holes, this time we have a few more filters. So we can filter based on the hole type, so blind holes, through holes, and complex holes. The cross-sectional shape of the hole, so circular or non-circular. and also filter by the size of the hole. So you might have a hole which, in a plant layout that someone could fall down, or something visually noteworthy. Then we don't want to remove the holes which are too big. So we're looking to remove small holes here, sort of the ones left behind by nuts and bolts. If I zoom in here, just to sort of highlight how much complexity these holes add. These are very small holes, and you can't really see them when we're looking at the model as a whole. But here you can see the amount of small triangles which are required to capture all that extra geometry. And there's a few examples. There's these small holes here, and all around the model you can see this the added triangles which we want to get rid of. We don't really need these holes, so it would be good if we could get rid of them and decimate over. So here we'll go for any hole shape and any hole type, and we'll search the model for those small holes. And once it's found these small holes, it will highlight them all again in red on the screen. You can see we found 150 holes here, which is quite a lot. And you can see they're all very small holes under an 11mm 2D bounding box size. And again, if we just hit fix, then it will remove all these holes from the model. And as you can see in our mesh set list in the top left, we've now gone down from 41,712 triangles to just 18,000 triangles, and our model still, is retained a lot of sort of the aesthetics, the visual traits. It's very obviously the same model, but with far fewer triangles, much less complex mesh. So the next tool we'll look at is the removal of protrusions. There aren't really particularly many protrusions in this model. This tool's really for sort of removing things such as embossed text, but there isn't much here. But we'll run the tool anyway, and it will pick up a couple probably. So as you can see, yeah, we found 3 different protrusions here. I think this protrusion is actually covered by one of the holes that we filled in, but nonetheless, it's found that protrusion. And again, we can just hit fix, and it will remove these from the model in the same way as the holes. So the next tool we'll look at is the removal of internal features. So here, we're probably looking for sort of the internal triangles which make up the structure. So you can see there's these 2 sort of legs sticking out on the left-hand side. If they're sort of hollow shapes, then there's lots of triangles on the inside that we just don't need, as well as down the shaft in the middle of the model. There's probably a lot of triangles on the inside of that that we can't see, so we just want to get rid of to reduce the triangle count as much as possible. So here you can see, yeah, down the middle of that shaft, there's a square there where 2 plates are touching, and we can't see what's on the inside. And on the inside of those structural components in the legs. And we found 1,912 triangles. And again, we can just hit fix, and it will remove these from the model. So at this stage, we can see, yeah, we've gone down from 41,000 to 16,000. And if we compare the meshes of these two representations, you can see, they're not massively dissimilar. It still makes it the same model. Still very obviously the same, but with a fraction of the number of triangles. But we can take this a little bit further. So again, we have our sort of crude simplification tools such as the wraps. So we can apply these wraps to small bodies under a certain size or to a selection. What we'll do here is we'll just go with the default, which is the convex wrap, which keeps less detail than the shrink wrap, but isn't quite as crude as a box. And again, we'll do it under a certain size. So we'll identify a component, a smallish component, and measure it. And again, if we click OK, it will return that value. And again, just hit find, and it'll highlight all of the components under that size on screen. In this case, we might want to filter our selection. So we found all the components under that size, but we might decide that some of them aren't appropriate for wrapping for whatever reason. So we can go into our filter, and we can go through one by one the components which we're planning to wrap, and they'll again be highlighted on the screen. So let's set that previous component, and we decide we don't want to wrap this component. It's maybe it's a key component, or it's visually striking and we want to retain some detail on it. So we can move that to the reject pile and continue processing as normal. So again, if I hit OK and then I hit fix, it's processed 13 of those 14, and it's left that one that we've moved to the reject pile. And as you can see, we have a simpler representation of all those components. But we can also do this on specific components. So if we identify a component, if we go to our mesh tree, and we can identify sort of very complex components, so maybe some specific problematic component. So here we have this body here, and that has 3,296 triangles, which is far too much for our target. So we can select that, and it's highlighted in the tree. And if we change our wrap settings to just process our selected components and hit fix, we can see we've turned that complex component into a much more rudimentary shape. It's very, very cylindrical, and we've reduced that from over 3,000 triangles down to just 202. But again, we've retained the aesthetic of the model. It looks very similar to before, but again, just removing triangles to make it a lot more appropriate. And the last tool we'll look at is the decimation tool. So again, here, no actual defeaturing. We're not removing anything from the model, but we're just replacing the triangles with less triangles to try and drive down that triangle count even further. So again, we can apply these rules to the whole mesh or across each part. We can set our maximum geometric change, and we have our target values. So here, let's just set our maximum geometric change to 0.1 millimeters. we'll stick with applying this to the whole mesh and across all the components. And we'll hit apply. So we've decimated 21 parts. They're highlighted in red on screen. As you can see, we haven't decimated all the parts just because those components couldn't have been decimated within that 0.1 millimeter tolerance. And we've reduced by just a couple thousand, so not up to the 70%, but that's because we had that safeguard of that maximum geometric change to stop us from oversimplifying our model. We say that might not be enough, so let's increase this to 1 millimeter again and hit apply. We can increase this as much as we want. But obviously, the more decimation you do, sort of the cruder the mesh will be. So you can take it too far. So in this instance, we've gone down to 3,000 triangles here, which is great, but we might decide that that's not enough triangles and that our shading in our downstream application might suffer for that. So we might not want to go too far, so we can undo that and maybe set a more appropriate value of 0.5. So that's our full process, I'd say. We've used all the tools now. We've taken our complex mesh with 41,000 triangles and we've turned it into a much simpler representation requiring just 4,000 triangles. It still, it still looks like the original model. And, this might be perfectly acceptable for integrating into a plant layout or whatever our application is, or for a low level of detail in a VR application. And if you just compare maybe one component between the two representations, let's look at this component on the end. We've got a lot of curvature here, so the only thing we've actually done to this component is the decimation. But as you can see here, the shading has suffered slightly, but not significantly. And if we can go into our mesh tree, we can compare how many triangles make up that component in each of those two levels of detail. So here, this is 264 triangles compared to the original mesh, which had 1,546 triangles. So quite a significant decrease in the number of triangles to represent that component, but visually, not too much difference between our new defeatured mesh and our original mesh. So that's great, and we've seen that we can, defeature our models now to produce a more lightweight version. But obviously, that was heavily interactive, and we don't always want to have to do that. We don't want to have to go and do that by hand each time we have a model. So what we can do is automate that whole process and apply all of those tools as we create the mesh in the first place. So if I just delete this mesh that we've created, and we'll say, we'll pretend that we're starting this process again, but instead this time we'll create those levels of detail during this create process. So here we've turned on our LOD1 and LOD2. And if I go into the settings, you can see here for our LOD1, we have our MES resolution controls, but also our simplification options. So I can select any number of the tools, and these mirror the tools that we just looked at. So we can turn these on the left-hand side. So here we're just doing holes, internal features, and decimation. And for our more crude LOD, our LOD 2, we have all the tools turned on, and these use sort of different values. We can change those values by hand to have something specific for our case. But in this case, we'll just go with the standard ones. And once we've changed these settings, we can save them. So we can save these to a configuration file. So next time you go into process and model, you can load that configuration file. It will have all of those tools and tolerances that you've saved. Or we can use these configuration files for the batch process. So for our command line batch process, you'd come in, you'd create one of these configuration files, and then you point to that configuration file, and it would use those tools and tolerances to process a number of models at the same time. But for now, we'll just we'll mesh at these two LODs using those tools. So I skipped a little bit of processing time here in the video. So it will only take a few seconds, but in real time, this took, I think, just over 60 seconds to produce all these LODs. And if we compare the models that we now have in our mesh window, so we have our very dense mesh, our LOD 0 mesh with 41,000. We've created this mesh 2, our LOD 1 mesh, which is 7,000. Much more appropriate for maybe a visualization application like in VR, a fraction of a triangles, but still looks very similar. And again, we've created our mesh 3, our LOD 2 mesh, which is our sort of defeatured mesh, and that only has 2,203 triangles in, which is much more appropriate for some of these visualization applications. And it's done all of that fully automatically. And just to flick through and show these LODs that we've created. So once we've generated our LODs, the last thing that we have to do is export them. So if we go into our export panel, here we'll just go out to FBX. It's probably one of the more commonly used ones for visualization applications. We're going to turn on export to multiple files. So that will export each one of these LODs into a separate FBX. And hit export. And the exported files will be appended with a suffix so that you have the file name and then the LOD 0, LOD 1, or LOD 2 after the file name. So this will only take a second. And we'll compare our exported files in our file browser. So here we have you can see we have our original step file, and we've produced these 3 FBX files, and I'll open one of these up. So we'll open up our LOD 0 file, our nice sort of very accurate mesh, and then we also have our LOD 2, our most defeatured mesh, which is a fraction of the size and a fraction of the triangle count. And just to compare these, you can see here still 41,000 polygons. And we have a nice mesh model, but slightly slow to render. And our much more lightweight file, so just 300 kilobytes, much easier to maneuver and visualize. So if I go back into the software quickly, and just to sort of reinforce the effect that these defeaturing tools do have, obviously you can just create a more crude mesh without applying any defeaturing tools. You could just mesh at a very high sag and turn, but you wouldn't get anywhere near the sort of balance between the visual result and the triangle count that you can get by employing these tools. So here we have our low LOD, 2000 triangles. Let's add another LOD, and we'll turn off the tools. And we'll use very sort of crude mesh resolution controls. So a very high turn and sag value. And if I mesh this, you can see that, you know, all of those round edges have been squared off. It doesn't look particularly nice, and even still, it has 4 times the number of triangles than our defeatured mesh. And even if I tried to sort of decimate this 9,000 down to match that 2,000, then we're actually just left with quite a mess. It's not a good looking model. You know, that's horrible. It doesn't look like the model that we had originally. And even still, that has 2,300. So that still has more triangles than our nice LOD2 mesh that we created. So that's just to sort of reinforce the benefit of employing these defeaturing tools. This is our nice mesh created by CADfix using our defeaturing tools with 2,000 triangles. And the one below is, you know, if you don't use any of the defeaturing tools, it's a mess, and you can't retain as much of that visual quality that you get by doing things such as hole removal and internal feature removal. So that's just a short demo, sort of to reinforce sort of the impact of using defeaturing tools whilst prepping your CAD geometry for visualization applications. So just to reiterate quickly, because I know we're quite short on time now, just to summarize the value proposition, we're here to streamline the conversion and simplification processes required for repurposing mechanical CAD assets for VR, AR, and MR, or more generally, visualization applications. We optimize and automate this MCAD to XR workflow with automated defeaturing and mesh generation, as well as batch capabilities. And this helps us to reduce project lead times and to save costs. And we can do that through our key capabilities, which are multi-CAD import, high quality mesh generation and optimization, intelligent defeaturing and decimation, the retention of hierarchy and model properties, exporting to multiple VR formats or multiple mesh formats, and doing this all fully automated for command line batch processing. So yeah, thank you for listening. Yeah, thank you for taking the time to join our presentation today. If you want to get started with CADfix Viz as a next step, or just play around the tool and see the sort of benefits of employing these defeaturing tools for yourself, then please register for a free evaluation at that link. Or just generally for more information, feel free to contact us using that email address or any of those phone numbers. And that's it from me, I think, apart from the Q&A, Kristen.
Thanks, Elliot. I know we are a little tight on time, but I do want to take a few quick questions. So if you do have any questions, please direct those to the questions window. For any unanswered questions we will have an expert follow up with an emailed response. So first question is there a limit on model size you can handle?
So no, there's no actual limit on the size of the models that we can handle. You can import any size up to gigabytes of data at once and process that. Obviously, though the larger the model, the longer the processing time will be. But no, there's no actual limit to the size of files that we can handle.
Awesome. Next question. Can you explain how to best automate the process?
Yes, so as I showed in that demo, when you save your configurations of tools and tolerances, you get this configuration file. Obviously, we can generate those logs automatically, like I just shown in the interface, but to sort of further that automated process, we do have command line batch capabilities, and it's very easy to set up. All you need is a very short script. You basically point at an executable in the program files, you point to your configuration of tools and tolerances, and you point to some models, and then that will all run in the background. So no need for any sort of user interaction, and that will dump out some your simplified FBX or whatever format you're using files at the end, as well as some log files on with some information on what's actually been carried out during that batch process.
Great, thank you. Next question is, what is the licensing options for this product?
Yes, so we're quite flexible with licensing. So we can have node locked licenses, server licenses, so LAN and WAN licenses, and different configurations as well. So different imports and exports, so you can build up the products that you need. Yeah, so we're quite flexible with our licensing. For more information on that, the best thing to do is probably to get in touch and talk to one of the CADfix Viz representatives from ITI, and they'll provide more information on that.
Okay, we'll take one more question. Do you need a powerful machine to run the program?
No, you don't. Obviously, the more powerful machine you have, the quicker it might run. But I mean, for example, I run this just off of my laptop from home, and that's fine, and it doesn't take too long. So there's no specific powerful machine you need. You don't need a high spec PC. Yeah, it should just run on any sort of standard PC.
Awesome. Thank you, Elliot. And thank you all for joining us today for our CADfix Viz Converting CAD to VR Ready Mesh webinar. I will send out a link shortly for you to rewatch this presentation. If you do have any questions, please feel free to email us at the info@iti-global.com email address, and we will be in touch shortly. Thank you so much and have a great day.